Good to see everybody. Appreciate you taking time and jumping on this tour. My name is Jason Davis. I'm an assistant professor with the Division of Agriculture. I work primarily in remote sensing and pesticide application, primarily drones, satellite imagery, and then sprayers. And we'll be talking a little bit about the intersection of those two today.
And I'm Dr. Terry Spurlock. I'm a professor and extension plant pathologist, but in addition to doing the traditional applied work that we do in extension plant pathology, I also operate in the precision ag and ag tech space and work a lot with Dr. Davis on robotics and automation and utilizing those data for plant pathology applications.
So the title of our talk today is So You Bought a Spray Drone. And what on earth does that have to do with robotics? Well, technically, these drones we see on the table over here and the big spray drones you have are really the first wave of commercialized robotics that we see in the agricultural industry. When have we ever walked out into a field, pushed a button, and let something go work for us? Now, my son, I pay him $20 and he mows for me. But that's a little different than the actual electronics that we're using in today's production systems. And those spray drones are that first wave. And so with that comes interesting new challenges in our industry.
Well, and the biggest of those challenges is we don't know very much. That's where we are right now. And so the goal of the work that we do, and we're pretty fortunate that we've been funded by the commodity boards as well as like Cotton Incorporated. So we have work on corn, cotton, rice, soybean, to really understand the new wave of robotics that's coming into the ag industry and whether or not that accomplishes those in ag that are purchasing or accomplishes the goals of those in ag that are purchasing.
And with those opportunities, we've been very appreciative of the foresight of the commodity boards, the corn board, the rice board, and the soybean board. All three have supported our programs to let us pursue the questions that the industry needs to look at. Primarily, how does these pesticide application systems, these spray drones, how do they fare compared to a traditional aerial application system? How do they look compared to ground-based spray application systems? And a lot of our work focuses on that. What do the patterns look like so that we can make sure that we're optimizing these systems to get the efficacy and the dollars out of every chemical droplet and every gallon that goes in that field?
Yeah, and I think it's important to understand that there's been a rapid adoption of spray drone technology and robotics in the ag industry, not just in Arkansas, but across the nation, around the world. And so it's important for us to understand those limitations of this technology, and that's what the research is designed to do. I did just this afternoon, I'll leave here, and with the county agent from Lonoke County, we'll go and we'll rate disease on a corn trial that we sprayed with a spray drone, a fungicide trial, just a couple of weeks prior, to understand if we're getting the kind of efficacy, and also get the fungicide, the pesticide, down into the canopy the way we'd like to see it down in the canopy from these drones, so that we can take those data and immediately extend it to our growers over the next winter, and they'll understand whether or not this technology is working the way they expect it to.
An early analysis, this is year one, so we don't have a lot of hard data right now to stand on, but so with first year information, what we see in the field, it looks really good. These systems are actually doing, if set up properly and that pilot understands how to apply chemicals, they look really good. A lot of our trials, actually, you can't tell a statistical difference between an aircraft application, a drone application, and a ground rig. Now that may not carry over to all applications and all systems, but right now what we see so far looks really good. But there's some other limitations in this. It's not just how good is the chemical doing. There's other physical engineering limitations, political limitations.
Well, and as you can see, we have a robot here, but we don't have the type of robot next to us that sprays a field and flies through the air. And that's because right now, as a Division of Agriculture employee, I can't purchase one. And so we're in the testing phase of actually the domestically made, the American-made platforms. And frankly, we're very, very early into that process to understand how they stack up to those that have traditionally been used that have been sourced from countries like China.
Yeah, and it would make a lot of sense for us to have somebody in the industry that we partner with, because we work with a lot of folks with spray drones, but guess who's all in the field spraying today? And so we couldn't actually get anybody here to help us out. But you know, even if you look whether it's a Chinese drone or a non-Chinese drone, a domestically made drone, there's some still significant limitations. Battery life only lasts so long, payload limitations, certainly when you're flying a craft based on electric power, has its limitations. And then from a regulatory standpoint, there has to still be a person to ensure the airspace safety in that situation. And so those limitations kind of take away some of the excitement around robotics and ag like we might have envisioned. We see opportunity in that though.
Well, we do see opportunity because what do we want robots to do? We want them, we have a saying in automation, automate the boring stuff, automate the repetitive stuff. So we want robots to help us accomplish more easily, maybe cheaper, those things that we're already doing. So in our case, we're testing on the plot level robotics in a research environment on research stations to extend those data and scale it to commercial applications. But we're also looking at those commercial applications by putting trials in farmers' field. We're also working on the next phase of robotics that, well, roll on the ground that we can use in our own programs to make our research in other areas less expensive.
So with that segue, we'd like to do a demonstration. This is a home-built robot right here in the Division of Ag. What you're seeing is a ground-based system. Currently it does not have an implement attached, it doesn't have a sprayer, but it has the ability to execute plot work. So it can actually, it's got relays on board, so you can just say, hey, I've got 4 treatments and 4 reps. Go to the field and spray for me, and it will do that. Right now we've got a camera on the belly of it, so we can actually go out and do data collection. So whether it's stand counts, vegetative height with LiDAR, there's lots of opportunities. The nice thing is this has got a battery on it that'll run about 2 hours. We can put a small gas engine on the other side to run for about 10 hours autonomously. Currently there's no regulations limiting its fully autonomous use, so as a demonstration, I'm connected to it on a cellular network. If I was a faculty member on campus and I needed to go collect data in my plots at here or Stuttgart, and this was plugged up at the station, I could say, hey, PlotBot, take off. And remotely, through the cellular network, it'll take off and navigate the plots that I've loaded up and fully autonomously collect that data or spray those treatments if somebody's there locally to actually load up that chemical. So this very brief demonstration, and I'm going to get out of its way, is fully autonomous.
Would it have hit you if you didn't move?
That's a good question. We actually have onboard systems that are object detection that are looking for people and vehicles to avoid. And we also have an onboard LiDAR system that will see things that are not people or vehicles. We currently have them disabled because as many people and vehicles as we have here today, it would disrupt the demonstration. But yes, the idea is in the field, if you have a crop consultant that pops up unexpectedly, it would stop and recognize that. We're assuming we're on beds today, so it's actually backing out of those beds without crossing them, so we don't damage the beds. There's different settings. If you've got drilled beams or something, you could actually turn in the field. It can navigate and actually do broadcast applications if you wanted to do that. And so broadcast, automated plot work, beds, no beds, we try to provide the flexibility that our researchers need to deploy these autonomously. We're going to go over here to the second alley. We're running at about 20% throttle. It can actually run about 5 times faster than this. Don't want to do that in front of a crowd this morning, so we've slowed it down a little bit. But again, it's doing it completely on its own. And in a second, we'll show, once it backs up here, on that screen, you'll see the data that we just collected. Now, there's not much value in it right now, but if this was your research plots and you were doing it from Fayetteville, then all of a sudden that's pretty valuable information. And so we look forward to hopefully having this on experiment stations and research stations and extension stations in the very near future, prototyping and testing, and hopes to bring this cost-effective solution to our faculty members.
Questions, comments about the robotics that we just discussed and the demonstration?
How dry does it have to be to operate? Like, will it be able to go around or go through stuff?
So most of our efforts so far have been on the coding side of things, intelligent navigation, safety features. The chassis is a prototype so that we can flesh out the errors there. This is a version 2 chassis. As you mentioned, it's probably not going to run through a flooded rice field right now, right? So ideally, we're looking at dry fields, dry beds. We haven't got it stuck yet because we haven't pushed it into those areas very hard yet. So I can't answer that honestly. But again, as a prototype, we're pretty pleased with, in areas with the canopy of certain height and certain dry conditions, we can navigate those. The other side of that the opportunity where it gets wet, we can use potentially a drone, but this can run ideally, 10 or 12 hours and either put out a chemical or collect data without you standing there on the turn row with it. So in this context, phase 1 of robotics, the drones, are pretty exciting, and those limitations are quickly getting worked out. Engineers are doing a great job of trying to work through improving battery technology and chassis and payloads and all those things. But there comes a point when it makes sense to go back to the ground and have the autonomy and that access on the ground. And so we hope that we're trying to move both systems in the right direction with good research and development.
And it's not just from a regulatory standpoint, right, with the FAA or whatnot, with a drone that flies through the air. But there are challenges with actual imaging. There are challenges with light. There's challenges with clouds and shadows and things like that. So a platform like this, collecting data, may give us some advantages in sort of teasing out some of those things that would confound data and actually allow us to collect data more consistently and more frequently.
Or different types of data that we traditionally do in the field manually, right? And so if you've got a research project in mind where we need a specific implement to collect a certain amount of information in the field, we can do that spatially at some level of scale, hopefully in the near future. So there's some cool opportunities there for collaboration.
And I'm fond of telling, when I talk to the boards about my project and I'm speaking about these autonomous applications, I'm fond of saying, if you give me $1 of funding, I want to give you back $1 of data, right? But when we start automating, we see in the very near future that $1 of funding may result in $1.50 back data, right? We can just do more with less, and ultimately that's the goal.
All right, I think we're pretty close to on time. Thank y'all.